Hi, welcome to our third unit in computer science, data structures and algorithms. I'm very excited to share with you one of my favorite data structures, the binary tree. We're going to look at binary trees and tree sets, tree maps, and heaps made with trees. So we've got a lot to cover in this unit. But before we go too far into it, we're going to just spend this lesson talking about some vocabulary. Big new words, lots of new ideas coming at you in this lesson. So let's slow down a little bit before we get to the code and just practice understanding how everything is. We're going to talk in a lot more detail about graphs in a later unit, but I do need to cover a little bit about graphs before we go into binary trees specifically. So what I have here is just a simple graph. Okay, so a graph is a node with edges connected. So the nodes are these circles. Okay, I've got 1, 2, 3, 4, 5, 6 different nodes, and 1, 2, 3, 4, 5, 6, 7. Looks like 7 edges if I count that right. 1, 2, 3, 4, 5, 6, 7. So, a couple important things to keep in mind about graphs. This is called two different edges. You know, you might say, "Oh, that's just a point on a line because it's a straight line." I don't know. I can't tell if that's the same line or not, but you don't think of it that way. This is an edge that connects from one node to another, like a road. Okay, and that's another edge. It is possible to have more than one edge between two nodes, but that's not very common. We won't see that right now. Um, the These here are called this whole picture is called a graph. All right, these things here are called the nodes. Okay, so let me make that just a little bit more clear. There we go. That is a node. And we've talked a little about nodes with linked lists because basically linked lists used nodes, right? And the edges in linked list were the reference to next. So, and then this here, I'll highlight this one in red. This is called an edge. Okay. All right. One other thing to keep in mind about graphs is that if you have two lines that cross over, it could be that was just convenient for drawing purposes. If they don't have a node shown, uh, then they're not connected. They're like overpasses in a freeway. All right. So we got our nodes and we got our edges. Let's talk a little bit about some more vocabulary. I want to introduce another word called cycles. So a cycle in a graph exists if you are able to go around in a circuit. So, for example, here's a cycle. It's certainly not the only cycle. We could do another cycle here, right? And we could even do the probably the entire thing, right, in a cycle. Yeah, just missing this one edge in the middle. So yeah, anytime you have like a loop like that, that's called a cycle. Okay. So a tree graph is what we're going to be focusing on in this unit. So tree graphs are unique graphs because they do not have any cycles at all. So let's take a few examples of some tree graphs. You'll notice that they have this kind of like branching out. Like that's why they call it a tree because they look like a tree that with branches. This one here is you got like kind of a center node and they're going out in all different directions. But you'll notice there is no cycle. Once you go out, there's no way to come back in without backtracking. Here's another one. This one looks a little bit more like a tree, I think, because it's got a base and then it comes up here and with branches. But this one here is actually more like what we'll be talking about in this unit here. So it doesn't look like much a tree. It looks more like an upside down tree, right? And in fact, we'll call this the root. And these are the leaves. So they're kind of upside down, but we just typically represent it that way. Okay, so a rooted or directed tree is one where we have this root up here. Okay, this starts everything. Now notice there's a difference here in the edges. So in our simple graph and in here, these edges are just lines. Well, now these edges are arrows. So when we have arrows like that, what we're saying is that it's called directed. So if you're at what I'm calling node 1, you can travel to node 2, you can travel to node 3, you can travel to node 4. But if you're in node 2, once you reach node 2, there is no way to go back to node 1. We're not going that way. We're only going this way. That's the directed graph kind of way, if that makes sense. It turns out when we make these, we actually will, for our programming purposes, leave a connection. But when we're contemplating and thinking about how these work, we're going to think about going down. So with that in mind, let's label some things here. What are the We'll just use their node numbers. What is the root node? So the root node is this node that everything branches off of. So that's actually node number 1. All right. Now, nodes, you can have parent nodes and you can have child nodes. Most of the nodes in a tree will be both children and parents. The root node doesn't have a parent, so it's not technically a child. And the leaf nodes down here, the leaf nodes are the nodes we call the end of the tree that have no children. They're not technically a parent. So all of our parent nodes are 1, 2, 3, 4, 5, 7. The children nodes are really everything except for the root. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Those are all children. The leaf nodes are the nodes that do not have any children. So for us, that's 6, 8, 9, 10, 11, and 12, because there are no children from those nodes. All right. Okay, so what is a binary tree? Well, a binary tree is just quite simply a rooted tree, a tree where there's each node has at most 2 children, okay? So this last one is not a binary tree. You can see the root node has 1, 2, 3 children. See, binary by for 2 can only have 2. Now, a binary search tree is one in where the nodes, the leaf nodes and the children nodes are arranged in such a way that they're sorted. So the idea of a binary search tree is to keep things in order, okay? So let's consider the following characters, C, D, F, A, E, B. Let's put them into a binary search tree together. All right, so I'm going to start with, we'll just label those with the letters. We're going to put them in an alphabetical binary search tree. And I want you to imagine they're being added in this order to the tree. So the first node we get has to be our root. So we'll just put a C there. Now, the next letter I get is a D. And so alphabetically, D comes after C. We have to put it as one of our children, but I'm not going to put it as the left child. I'll put it as the right child because D comes after C alphabetically. So we'll say D. All right, now I get to the node F. Well, I start again at the root. F comes after C. So I go over here, and then I'm at another node, and I say, okay, well, F comes after D, so I go right again. So you kind of see how I'm doing that, right? All right, let's go back to A. Okay, I start at the root node, because that's the point of entry to the graph. Now, A is less than C, so I'm going to go to the left, and that's where I'm going to put an A. Then I need to put an E. Now, E is after C. It's after D, but it's before F, so it's going to come here. So that's where I'll put an E. And let's put the letter B. B comes before C, but after A. Now, if we've done this correctly, and you'll notice that I did not make this branch here so big that it went to the right of the C. Sometimes that's hard to do drawing it, but it helps to imagine it this way. If I did this correctly, these should all be in order when I look at it left to right. And you can see A, B, C, D, E, F. And that's how it goes. So you can see the binary search tree is keeping some things in order for us. All right, I'd like you to pause the video and on like a piece of paper, or if you can draw on your computer monitor, not the monitor, but the software itself lets you draw on it. Then go ahead and try and create a binary search tree that keeps these integers in order from left to right. We'll be using 4 as our root node. We'll start with 4 and then we'll add them in order. So pause the video, give it a try. All right, let's see how we did. So I'm going to start with 4 right here. And then I'll slide to the right for 6. 7. Again, always go back to the root. Be imagining this algorithm that we're going to have to implement at some point. Slide to the right to 6. Slide to the right to 7 because 7 is bigger than 6. Let's do a 1. Well, 1 is less than 4. 9. 9 is bigger than 4. 9 is bigger than 6. 9 is bigger than 7. Let's do a 5. 5 is bigger than 4, but 5 is less than 6. Let's do an 8. 8 is bigger than 4. 8 is bigger than 6. 8 is bigger than 7. 8 is less than 9. All right, let's do a 3. 3 is less than 4, but 3 is more than 1. There we go. All right, we've got a root node at 4. We got some children here, the rest of them. The parents are 4, 1, 6, 7, and 9, and 3, 5, and 8 are leaves. Okay, what's next? All right, let's do a binary search tree for the letters in computer science. Now, some of these are going to repeat. Now, we don't typically do that, okay? We don't typically repeat letters in a binary search tree, but we do sometimes. And this time I want you to repeat. So anytime you have a node that repeats, I just want you to slide that node to the left, okay? All right, let's do computer science. Pause the video if you haven't yet, but if you're ready to move on, you've already tried it, then you can watch. All right, we'll start with a C. We'll take O bigger than C. M is smaller than O. P, C, O, P. All right, then I've got U. So U is bigger than C. U is bigger than O. U is bigger than P. All right, T. T is bigger than C. T is bigger than O. T is bigger than P. T comes before U. E. Okay, E comes after C. E comes before O. E comes before M. R. R comes after C. R comes after O. R comes after P. R comes before U. R comes before T. S. S comes after C. S comes after O. I think I might need to get some extra room. S comes after P. S comes before T. S comes after R. All right, C. We already had a C. So we said slide to the left. And if, we might have had something else on slide to the right, but here we'll just have two C's in a row. I. I comes after C. I comes before O. I comes before M. I comes after E. I. E. E is a repeat, so we said we'd slide to the left. So this is supposed to be to the right of that C, but it's okay. N. So N is less than O, but more than M. C. We already had a C, so it keeps sliding to the left. E. We already had an E, so it keeps sliding to the left. There we go. That is the binary search tree. We should have it relatively in alphabetical order if you look at it from left to right. C, C, C. Well, I say relatively. It should be. C, C, C. E, E, E. I, M, N, O, P, R, S, T, U. And there we have it. All right, so I want you to consider the following binary search tree. I want you to name the sibling node of D. So let's talk about sibling nodes. What would be I got some kind of rogue line there. It's bothering me. All right, the siblings are the nodes that are at the same height, and they have the same parent, okay? So that's what we're looking for. Two nodes that have the same parent. D is here. It has a sibling at A. So the sibling of D is A. Or you might say A and D are siblings. What's the parent of D? Well, the parent of D is B. And what's the child of D? Well, the child is C. We could say it's actually the left child. All right. Determine the depth of node J. So the depth is how many steps it takes you to get there from the root. So like most things in computer science, it's kind of like we start counting, but we start counting at 0. So the depth of E is 0. The depth of any root is 0. So that's 0, 1, 2, 3. The depth of node J is 3. The height of node B. Well, now height, we talk a lot about depth. We don't talk a lot about height, but it does come up, so we do need to talk about it. But height is actually how many steps it takes you to get to the leaf from where you are. Not the nearest leaf, but like your deepest leaf. So what's the furthest down you could go? So I could go to the left from B and it'd only be 1, but from B I can keep going to the right 1, 2. So the height of B is 2. That's the maximum amount of distance I can go to a leaf. So you just want to find B's deepest leaf and kind of count up 1, 2. Note that the height of any leaf node is 0, right? Because the height of A, how far do I have to go up to get to A? Nothing, 0. Height of C, nothing. Height of D, though, would be 1. Height of B is 2. You get the idea, right? All right, what is the height of the tree? Okay, so the height of the tree, I got to find the deepest node, okay? So the height of the tree is the height of the root node, okay? So 1, 2, 3, 4. That is the height of the tree. That is also that is the depth. The height of the tree is also the depth of the deepest node. So you could start at the root and be like, okay, well, this node is 1, 2, 3. This has got a depth of 3. This is 1, 2, 3. This depth of 4. 1, 2, 3. 1. Oh, it's 2, right? Yeah, that was actually 3, not 4. This is 1, 2. Sorry. Try that again. So, what is the depth of A? So 1, 2. The depth of C would 1, 2, 3. Depth of F 1, 2. Depth of H is depth of I is 1, 2, 3, 4. So yeah. So the height of the tree is the same as you can start at the root and see which one's got the highest depth, or you can find the lowest node and count what the height of that lowest node is from the root. They should be the same thing. What's the root of this tree? Well, that's node E. Let's name all the leaf nodes. Now, the leaf nodes are the nodes that have no children, so that should be A, C, F, and I. One of the things that's important to remember about binary trees is we're going to learn that they have relatively quick insertion time as long as the tree is balanced. So on the left is a balanced binary tree, and on the right is an unbalanced binary tree. Do you see the difference? So keeping a tree balanced is kind of tricky. There are several different ways to do it. They're called, one of the most popular, I think it's called the red-black binary tree. We're not going to be talking about that right now. We're just going to be learning about binary trees, but that would be a kind of a future discussion. So yeah, we would prefer to avoid this situation if possible. You may have noticed how just distorted this was. Part of the problem is that we started with the letter C, which is so early in the alphabet. That's why that computer science one was so weird. All right, so there's something called full and complete trees. Now, a full tree is one in which there's not a tree, there's not a node that doesn't have two or zero uh, children. So this one here, this is not a full tree, but it is what we call a complete tree. A complete tree is one in which you assign children from left to right. So we started with this node, and then we fill in its two children, and then we go from left to right. This node gets its two children, then this node gets its two children. You see, we're kind of halfway done. The next one that we get, if we have to add another thing, another node, this binary tree like that. So that would be a complete binary tree. It's pretty hard to make a complete binary tree that's also a search tree, and they don't really are used that way. But we'll use complete binary trees for some things, and we'll use binary search trees, which are not always complete, for other things, right? But a complete binary tree is perfectly balanced. It's the most balanced you can possibly have at any given time. So that's a good tree. All right. So that's it. That's my covering of binary trees. So what is it that a binary tree is going to allow us to do? Like, what you may have noticed when we did linked list and array list is that, array list allowed us to add at the back really fast, right? O1, constant time. We could remove from the back. We could access any element really fast. The linked list allowed us to have O1 time at the front and the back, removing and getting and adding both to the front and the back as long as it's a doubly linked list. So that was really cool. But we lost with the linked list, we lost that quick access to the middle. But neither a linked list or an array list worked very fast for removing in the middle, right? They were O in, or real sluggish O in. So what we're going to learn, though, is that the key to doing things quickly, where you got to find something in the middle fast and access something in the middle fast, is to keep it organized. And that's what a binary search tree does. It essentially keeps things alphabetized. We already know this. We know that if things are alphabetized, I can find them more quickly. We are going to get some cost to that, though. The binary search tree is going to allow us to have quicker than O in removal. We're going to finally get O log in removal from the interior. But we're not going to get the O1 access that an array gives us. We're still going to have O log. We're going to have O log in access as well. So it'll be a little slower to access than an array, but not much because it's still really fast. Login is very fast. But we do get that O login removal that we've never had, and that's really super cool. We won't really have like a front or a back, so it's going to be O login removal everywhere. So that's the kind of the pro and cons in a nutshell. The advantage allows me to remove and to add in the interior very fast. Keeps things sorted, so I don't have to call a sorted algorithm. It already is sorted. It's just have to traverse it. So that's nice as well. So those are the kind of situations where you want to keep a binary search tree. I mean, talking about, hey, do I need this fast access to specific values? And do I need to keep that? Am I going to be having to need it sorted at all times? So if you need something sorted and you need fast access to the middle and interior of a set, a binary tree is the way to go. All right. I will see you in the next lesson.